Hello. What we have here is, I don't know what you want to call this episode, but it's a combination of all my other episodes. I have a grid tie inverter which I repaired. I've added an external 110,000 microfarad capacitor to smooth out the ripple. I have two buck converters. One's a master and the other's a slave, to reduce the grid tie panels from 60 volts down to around 20 volts that the grid tie inverter can use. This particular one has an adjustable setting, so under a certain voltage the controller turns off, so you throttle back the grid tie inverter and maintain power point. This is one of those power meters, GT130As. This is one of the $8 ones, and this has some display problems. That often the display comes and it's hard to read. That's because there's no contrast adjustment. I've added a contrast adjustment here, and then you can get a real nice clean display. This is only good for up to 60 volts, but I've modified it with a voltage divider. In these resistors, I have a switch so I can measure the high voltage and the low voltage. This thing now will monitor up to 600 volts DC. And this is probably what I really want to talk about. This is the diversion controller to heat water. I mean, we have a water heater sitting right next to us. And what this is a standard 3525 inverter board that you can buy on eBay for about $4. Inverter boards operate just the opposite of what a diverter would go. An inverter board, once the bank voltage gets up to a certain volts, it turns off. And in diversion, you want it to draw as much power as possible until it gets down to a certain voltage. So there's a number of modifications that are done with that. As you can see, it's just this board, and then we're driving 2 FET over here, and this wire goes over to the water heater, and that's your dump load. And right now, you can see I'm not dumping any voltage into it. I've been diverting all my power, which is not much right now. I have a 560 watt array outside that's covered a little bit by shadows, and it's a pretty cloudy day, so we're only getting like 160 watts right now. Just about a half hour earlier, I was getting close to 500 watts out of the entire system. Just shows you how much things can change during the day. So on this one, all you need is the inverter board, a couple of FET. I buy these, this little power supply costs less than $1.50 shipped on eBay. They're rated at 120 volts input AC, but they'll work fine on 50-60 volts DC. Some of them work right out of the box, others require a little modification. It's in my videos. And this is the capacitor bank. These are 1200 UF each, and that's for the inverter and the dump controller. You need some capacitance. I prefer to see like at least 2,000 or 3,000 minimum. You know, if you're pumping out a lot of current, you want to go up to maybe about 10,000 microfarads. So here's our adjustment pot. Right now we're up at 59 volts. As you can see, I can drop the voltage a little bit, and then power is being diverted to the water heater. And we'll go back. and it takes a while for the grid tie inverter to turn back on as it's searching for a power point. But this will go back to 0 as the grid tie inverters spool up. This is the basic schematic of the system. As you see, this is our control board. This is the adjustment pot. You got to figure out what resistor here you want to use, but the formula is down here. This is your water heater, capacitor bank, and this is that little supply. Now these can be tied into a charge controller, like if you have a PWM. Anytime that PWM is off, there's power that you could use, but it's just being wasted. It's not being used. Adding this diode is optional if you have a charge controller. This capacitor bank can supply a lot of current, and normally solar panels are current limited, but if you supply a big capacitor bank on it, it can supply upwards of 10 times the normal current that the charge controller would see, and the internal FETs will pop. So be aware, add that diode. This is the modification sheet. This is the way the inverter board was wired initially. This down here is the modification to operate an external temperature controller that you can buy, just a relay contact. The voltage sense pin, this external 100K resistor is soldered on the back of the board, and this reference pin, a transistor that was right here is removed, and the resistor that you take out of from up here is placed in that, so you're not buying any extra parts. There's a latching diode that must be removed, that's D4. What happens is anytime it goes into overcurrent with an inverter, it'll just shut the thing down, and you manually have to reset the switch. If you have an inverter, you know what that's like. Anytime you overload it, you have to reset. We want to remove that because we're going to be turning this pin on and off with an external temperature controller. And these things normally operate about 25 kilohertz. You want to get it down to less than 1,000 hertz. So you're not having any excessive heating of the FETs. Every time a FET switches from on to off or off to on, there's some transitional heating done. There's no need for operating at those high frequencies. You know, 120 hertz, 150 hertz is more than fast enough to switch. This gets you around 380 hertz, if I remember right. But that's the system, and it's working quite well right now. The power has gone up. We're at about close to 200 watts going into the grid tie, and we're putting about 7 watts into the water heater. Water heaters, normally you have to supply around 50 watts into them all the time just to maintain temperature. So actually diverting about 50 watts is quite useful. Well, I hope you found this interesting. Thanks for listening.